Hello, we are Group 2 presenting our second project of SER502. In this project, we have designed MYST programming high-level language, corresponding intermediate language, compiler and runtime environment. MYST runtime and compiler are designed in Java. For compiler design, we have used Antler 4 tool for parsing and lexical analysis, and we are implementing a stack-based intermediate code. MYST programming language is powerful enough to perform condition constructs, loop constructs, data structure, and recursion. Further ahead, we will be providing some example displaying the mentioned features. Ahead, we will be running a Fibonacci series code using recursion and a code implementing stack. Fibonacci series code will also display the use of condition statement, whereas stack will display the use of loops. Some of the key features of MYST can be described as static scope and static scope checking. Static scope checking is where, whenever a variable is used, MYST compiler will check for variable in the local symbol table, and if not found, will check in global symbol table. It will throw compilation error if not found at all. Static type checking. For the static type checking, whenever a variable is assigned or is used in condition or expression statement, compiler will check if used data type is compatible with the variable declaration. This is done by mapping the variable to the data type of variable name during declaration. Type checking is performed on assignment statements, function parameter and return statement, and operations, that is conditions and expression operations. If type checking does not match, a compilation error will be produced. MYST program follows top-down parsing approach to parse and execute its code, meaning function definition has to be provided before function call. Similar to Java and C++, MYST programming language has a single entry point called main, command line execution for compilation and interpretation of code. The following table describes different constructs for MYST language and the example of how they can be used. For example, integer is numre, boolean is falter, and so on. Similarly, while loop is redo till, condition statement is cond and instead cond. Described in this slide is the corresponding intermediate code for high-level MYST code. We have stack-based intermediate code where stack, push, and pop functionality is used to perform all the operations. An example can be described as the division operator in the next code of high-level MYST language. In this high-level MYST language, division is the color-coded highlighted code is the division that we are focusing on. So the division operator is converted to div in intermediate code, and all the operations are performed through a stack by push and pop assignment only. Next few slides will showcase the various code displaying the several features of MYST in high-level language. Its corresponding generated intermediate code and the final output has been displayed as a screenshot. We will be skipping over few slides due to time constraint and will directly go to the error handling and will later implement these codes for the demo. The codes that we have skipped are condition statement, loop, recursion, and stack. For the error handling, we have implemented several error handling cases. For example, type checking in variable assignment, that is error 1. Type checking in method parameter passing, error 3. Type checking while using mathematical operation, that's error 4. Parameter count while argument passing to method, error 2. And static scope checking, error 5. If we run this file, we will get all these errors as seen in the screenshot. Now, for an example, we will run a Fibonacci series code, but this code has a couple of errors, and we will show how our compiler handles this error. For an example, in line 24, as you can see, numre a is equal to 5 plus z, but z has not been defined so far, so there will be a first error, and the second error will be in line 25, in which we are passing two parameters to the Fibonacci method, and Fibonacci method can only accept one. So if we go to command line and try to execute this code, we should get some kind of error message. So here is our two error message. As expected, variable z is not defined and function fibo accepts one parameter. Now let's go and remove that error and try to run the same file. So we'll be removing the undefined variable that is not required and the parameter that is not required. Now in this code we are looking for the Fibonacci's number 11, and it should be 55, but let's run it and see. So we have run the first compile and we got the compilation successful. Now intermediate code has been generated. Now you can see this is the intermediate code generated for a high level code, that is the Fibonacci series, and we can further go ahead and try to run this intermediate code. If we run this intermediate code, we get our answer 55, and that is the expected output. And this was the first example of our MYST code. Now second, we will be displaying the stack. So here is a high level code. We have for the stack, we have a stack named B. In MYST, stack can be declared by using the keyword pile. In this case, we are using a loop to push four integers to the stack and later popping and printing them. So let's if we try to run this particular code, it should be flawless and it should be a compilation successful output. And our file has compiled successfully, and let's see the intermediate code produced. And here is our intermediate code produced for the high level stack language. We can further go ahead and try to run this intermediate code. And when we run this intermediate code, and as expected, the numbers have been printed. As it is a stack, the numbers have been printed in the reverse order, and that means it is the correct, it is working perfectly. Next example is our expression code. In our expression code, we are trying to show our application of PEMDAS, and over here we are trying to prove how we have used an unambiguous grammar to correctly implement a PEMDAS rule. In this code, we are finding the value of n, and we get the first n from the main function, then we have a global value, then we are multiplying and finding the mod. So if we and we are adding. So if we compile this code, we'll see our intermediate code. And the compilation was successful. Let's see the intermediate code for it. And this is the output intermediate code. We can run this code. During the when we created this file, we expected the output to be 8 for that calculation, and here's the 8 answer, and expression file is working. Next, we are going to demo our source code for MYST. As mentioned earlier, we have used Antler for lexical scanning and parsing. Antler reads the grammar, which is defined in grammar.g4 file. As you can see, this is our grammar from MYST, which is unambiguous and left recursive, keeping in mind operator associativity and precedence. For generating intermediate code, we have created MyVisitor class, which extends Antler provided base class. Here we have our global and local symbol table to check for variable scope and perform type checking during compile time. Next is the implementation of runtime, for which we have interpreter.java, which in turn uses function.java for each function declaration. Here again we have implemented global and local symbol table to push and map variable value to variable which will while execution, and pop mapping once the variable is out of scope during runtime execution. This concludes our presentation, and thank you for watching.